My first question tells us that something has a weight W on Earth. What is that person's weight on another planet? Usually we'd say W equals mg. That's only good for the surface of Earth. We're on a different planet, so then we got to use big G, m1, m2 over r squared. Okay? And then I just now have to vary what they say to vary. It has a diameter 4 times greater. That means your radius is also 4 times greater than on the surface of Earth. And half the mass. So we'll take one of these masses and we'll half it. Doesn't matter which one. You have half your numerator. That has the effect of halving the fraction, or halving the value of the fraction, I should say. That's just an ugly looking 2, sorry. And the bottom, since you have increased the radius by a factor of 4, you've actually effectively, when you square it, increased your denominator by a factor of 16, because 4 squared is 16. That's supposed to be a 16. So 2 times 16 is 32. That would be W over 32. Okay, this is a bank turn problem, so I'm immediately going to go to a free body diagram looking sideways at it, because this is what we're used to. Here's your angle theta. You have weight going down, your mg. You have a normal force. That is supposed to be perpendicular to the surface. I don't think it looks too perpendicular, but you get it. We don't tip our axis for bank turns. It does not behoove us. So we keep them normal. Because I want inward, radially inward on my circular path to be on my positive x-axis. So this and this angle are the same. That makes the vertical component to n right here, n cos theta, and your horizontal component right here, which is n sine theta. Now redrawing this down here, you've got up n cos theta, you got down mg, and you got radially inward the sine component n sine theta. Once you've taken the n and it's represented it in its two components, you don't have to draw the n anymore. All right, now we get to our t-charts that I love so much. On the y-axis, you're not going up or down on the y-axis. You're really just going around in a circle like this. You stay on the y-axis. So you have sum of the forces 0 on the y-axis. That gets you to n cos theta, balancing mg. And I know I'm going to have to get rid of n because it is not a given. I'm solving for it. Equals mg over cos theta. Now on my centripetal axis, your x-axis, different story. That's a centripetal axis. So the centripetal forces is going to be mv squared over r. That's the formula for it. You have one thing on the centripetal force, that is n sine theta. It has to be equal to mv squared over r. Goes in right there. You end up with mg sine theta over cos theta equals mv squared over r. At this point in time, I can get rid of the m's. What am I solving for? Radius? Okay. Sine theta over cos theta is tan theta. So I go g tan theta equals v squared over r. Solving for r equals v squared over, just lost track of my thoughts. Oh, g tan theta. This one is where most people lost all the credit. You are not on the surface of Earth. If there's Earth, that's one Earth radius. You are 2 above that, going around a circular orbit. That puts you 3 r above or between center of masses. That's the radius of the path traveled. Okay? All right, look at all my answers, kind of giving me an idea where I got to go. At any point, The only thing keeping you going in a circle, if you're a satellite, is the gravitational pull pulling you down. Since you're not on a surface of the Earth, you can't use mg. You've got to use that centripetal force, which is the gravitational force, g m1 m2 over r squared, set that equal to centripetal force mv squared over r. Okay, now this is the mass of the thing in the circular path. That's the mass of the satellite. That goes. What's left is the mass of the Earth, which is why you see m sub e in all of these answers. I'm supposed to solve for the radius of the Earth. Okay, so let's start doing that. I see pi in all my answers. I'm going to get a new expression for v here because I don't see v in any of the answers. Since it's uniform circular motion and you're going at a constant speed, you can use v equals d over t. I'm allowed to use big T in my answer. That's the time to go around once. If you use that as a time to go around once, you have, oh wow, I'm not even in view. If you use that for time to go around once, you have to use the distance you went around once. That's circumference. So it's 2 pi r. Okay, so he said universal gravitational, we put the gravitational force equal to the centripetal force because it is the only thing pulling on it. And then over here, I said I see in all the answers. I don't have any velocity, so I'm getting another expression for that. I'm going to pull that in. So you've got, you know, before I pull it in, I'm going to square it because it's just easier to do it out here. If I square this whole thing, because I want v squared there, you end up with 4 pi squared r squared over big T squared. Now let's go over here. Right off the bat, I could see over here I can get rid of 1r. One here and one there. Okay. Now I'm going to sub in all this for that. So you have g, mass of Earth, over the radius of Earth. One of them canceled out. At the end, I'm going to plug in that fact that it's 3 Earth radius away and see how that changes everything. Equals, and v squared is just 4 pi squared r squared divided by big T squared. I'm going to multiply the right and left by r and divide by this over here and multiply by that. So we'll end up with g t squared. Oh, forgot about the mass of Earth. Stick that in here. I'll put it here. That's still up there. All divided by 4 pi squared equals r cubed. Now, let's plug in the fact that the actual r is 3. So when you pull that out, you've got to cube it. 3 times 3 is 9, 3 times 9 is 27. Divide through by 27, and this becomes r. It's going to be equal to the cube root of this, but you got me, big G, big T squared, all over, divided through by 27, 108. So you get 108 pi squared all under the cube root. That's how you do that one. Oh, let's just look at that for a second. Last one most everybody got. Wasn't that hard for most. Center of mass right there. You've got T2 coming up that way off of it. You've got, this is going to be a little ugly, but you got T1 pulling that way off of it, and that's mass. Mass times 10 is the force pulling down the weight of 2,500 newtons. Conventional coordinate system is going to do just fine for us because T1 falls on an axis and so does the weight. I just got to divide T2 up into its components. So down here, that would be T2 cos 30, and this would be T2 sine 30. T2 pulls against the 2500, T1 pulls against T2 cos 30, so I'm going to divide things up. X, Y axis. X axis you have pulling to the left. Remember, this is a static equilibrium problem. It's just hanging there. That means it's got to be balanced forces. That means T1 has to balance T2 cos 30, and 2500 has to balance T1 sine 30. So T1 equals 2500 divided by sine of 30. Sine of 30 is a half. 0.5, that's 5,000. Bring that number over here. Oh, these are all T2s. I don't know why I said T1. Sorry, these are all T2s. So T2 equals that, and this is, no, this is T1. Oof, I'm messing up. T1 has to balance T2 cos 30. T1, T2, got it. And then 2500 has to balance T2 sine. There it is. That's where I screwed up. T2 is 5,000. Plug T2 in there. T1 equals 5,000 times cos 30. Got to do that one on my calculator, which is 5,000 times 0.866. 1, 2, 3 times 0.866. 4330.